There we go.
Yeah, we'll take
All right, sorry. Let me start recording here so we have all this.
And you know, test questions, extra point.
Yeah, so even higher, right?
Let's go.
That's cool. Okay, so 4 gives you full credit here. There was one where it's just a tiny mistake here. So, or you had everything right. So there's like a 4 with a circle. I think just a few people got that, which was just minor, but good from there. 3, 2, and 1 is fine. So for Canon students, you guys can redo any of the Canon problems. We good? Can't do the 2 honor questions for redo, and then the honor students can do all of it. We good? Cool. Any questions there? So I figure if you guys can, and it'll be a quick turnaround here, but I want to get it back to you guys before. Let's see, it's gonna be due Monday. We good? For test corrections. So then we can go over the test on Monday and we can be done with it. And then we really move on to chapter 6 afterwards. Okay. So go from there. I just handed the tests back. So we're gonna go with chapter 6. Dun, 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 dun. Oh, that is. Let's see. That is a grant right here.
Can we move him like a little more forward?
Maybe you can sit in that chair outside.
It's not out of my. It's definitely there, but I don't remember what it was.
Okay. Let's see where we're at. We are in chapter 6. We're going to start chapter 6 lecture today. Awesomeness. It's called analytic trigonometry. That's what this section is, but it's really it's solving equations. Something you may have seen before. I'm not sure. But
I don't know what that word is on the board, so.
Is there more algebra-y than all the rest?
Oh, kinda.
Oh.
Let's cross our fingers. How about that? Yeah, let's do that. All right, let's jam with it here. So solving equations, that's it. That's kind of where we're at here. 6.1, solving trigonometric equations. This is fun. This is probably what you're going to do most of the time. We kind of came to the end in a sense, if you think about it here. We started with definitions. Remember that? We really put in chapter 5 was all about all the different properties. And raise your hand if you, let's see. 3 really enjoyed chapter 5, 2 was and then number 1 was like I hated it. So how about anywhere for 3? Like chapter 5 was pretty cool. I like that. All the interconnections between this and that, the other thing. Okay. 2. Yeah, sorry, all right, 3. Sorry, 3, 2, or 1. So okay, everybody's like a 2 and 1.5. Okay, we got a 1.5 in there. Okay.
Eat it.
Okay, so let's jam here. So we got a few things here. Don't need to write these down, but just kind of in your mind's eye, thinking about we're going to solve simple trigonometric equations. We're going to get onto factoring trigonometric equations. Some we're going to have to use the quadratic formula, and then eventually look at something that involves horizontal translation. Whew. So in mind, simple ones, factoring, quadratic formula, and then translating things around. But let's go back to algebra. How about that? Just in case you forgot, we got 2 different properties from algebra. Because remember those guys? Probably used them, probably forgot the name of them though. So it's called the addition property of equality. If A and B are equal to each other, I can add C to both sides and everything is great. I can still keep my equal sign. Again, write this down if you need to. If you know this very well, you don't need to write it down. We good? Because I see the people that write down everything. They're still writing it down. I was going to put Back to the Future, but it didn't make sense, so it was just back to algebra. So.
The future and algebra are pretty similar. So.
All right, multiplication property, of course, A is equal to B. You can multiply both sides by C as long as, I guess we should put this, as long as C is not equal to 0, right? That's the technical version of it. Can't multiply by zeros, but everything else is great. Ooh, you know what? I did not know. Let's see. I'm going to just try something here. Da-da. I did too. Cool. Okay. be able to walk around the room again. We'll see. Cool. Okay, we got good? Let's just practice real quick here. Let's go with the easy one, factoring one, and quadratic formula from algebra. We're good, just kind of practice sake, all yours there. If you have trouble doing this problem, then we're really in trouble. We're good? So we should be able to solve it. Or you don't remember. Okay, I'll grant you that. Where is mine? All right, anybody who gets it first, shout out the answer. If you're that excited about it.
Okay, cool.
Better? Yes. Negative 2/3 is a good, all that good. So you may have solved it a little bit different than me. This is the way I usually solve equations. I get my variables on one side, make sure variables are where they need to be first. And then I take everything else that does not have that variable to the other side. And then eventually divide through and voila, reduction if need be. And I think I'm okay with negative 2/3. We good? Okay, cool. Simple one. That's easy enough here. So, but really, in a sense, in algebra, we get to x. Is that right? So since we have a trig function here, we're going to get at least to the trig function. Now we'll do some stuff out of it here, but that's it here. So example number 2, all yours. Can you factor this or solve it by factoring?
Do you think I could turn this down a little bit?
Oh, absolutely.
It's very hot right on me.
Do it warm.
Or make it so it angles out.
Yeah, let me set the angle.
It's like a moving option. It's just like.
Thank you for asking. And not waiting till all the way to the end of class.
Just smarting.
All right. I've been looking at the algebra book. You guys went through the algebra book, the Jacob's book, the one that had, let's see, it had either the little geckos all around it. Is that the one you guys went through? Remember that one? That was fun. Uh-huh, the cartoons, yep. Out of curiosity here, did you guys, because we're looking at the algebra book now here, like the book? What was some good features about it? Is if you can remember it from like 2 years ago.
My favorite part about the book was how there was a green lizard, a magenta lizard, white lizard.
Uh-huh.
That's all I remember.
No, I think that was it.
My favorite part was probably when we got through the book.
I don't remember.
Oh, did you guys get through all the book?
No, I don't remember. I mean, I don't remember it being bad. I don't have any other algebra books to compare it to.
Yeah, sure, yeah.
I liked it.
Do you guys remember algebra? Like, yeah. I
Um,
remember. Yeah.
No, I think I'm probably the only one who liked geometry.
Oh,
I
okay.
like geometry.
yeah, same here. Algebra was just an excellent thing for my brain.
Okay, gotcha.
My brain was like, yes, this we can do. We can solve for x. Why does 2 + 2 = 4? I'm out.
You want to roast beef?
I'm sorry,
Oh,
Greg, you
I'm
haven't
gonna
moved because you were late.
Yeah, and like,
you can Harvard one or
We could do this.
something. Yeah.
I didn't really need this.
We're gonna see just for you. Test is right there. That's your test. And test corrections due Monday. All right, so you guys, let's see, you guys did it by something called the box method. This is the X method, but it's still the same thing here. It's two numbers multiplied to -8, add to -2. And those are the numbers there. You guys had to do like a, was it like a box and then you had an X inside the box and it was like four squares, is that right? Yeah.
That's still a new adjacent.
So this is the new improved version, or at least the new version.
I don't like that version as much as the box.
Yeah, I like the actual-
You like the box? Does that makes more sense? Gotcha. Okay.
Yeah.
All right. Let's see. Set each of them equal to 0. Is that right? And then we solve each of them, and we should get an answer of x is equal to 4, and x is equal to -2. At that point, we're done. Right, we're reviewing algebra. So we did the simple one just now. We did the factoring one, and then we'll do the quadratic formula.
Yeah. X equals plus or minus, wait,
No,
b
it's
plus or minus radical
X
X
equals
plus
negative b plus or minus
AC
square, or a squared minus 4bc
over
all
2a.
over 2a.
Wait, say-
Okay, I think Amaya wins the jingle. Do I have it written down? Yeah, I did write it down. Okay, so all yours for this one here. Let's say, I guess we should do it. The quadratic formula is, thanks to Amaya's song, is -b plus or minus the square root of b squared.
Squared minus 4ac all over 2a.
I had
If-
this Lego for like a day and I don't remember just being that.
All right, let you guys try it yourself. How about this? You guys should know that the one right next to x squared is a. You got the b value and you got the c value right next to it. All yours there. As you guys are doing the problem here, of course, got to tell you a fun story. So, man, back in the day, I went to Blockbuster to rent a movie. Anybody have gone to Blockbuster to rent a movie?
Yeah.
You have,
Really?
Amaya? Are you serious?
Oh, yeah. My parents.
Back in ancient times.
Yeah, the ancient times,
Yeah.
yes, when Aristotle was still alive,
Yeah.
something like
Oh my
that.
gosh, parents haven't seen them forever.
Centuries ago in the 90s.
Yes, the 90s, yeah.
Centuries ago, yes.
Yeah, it was cool. Let's see. So I'm just saying, quadratic formula sometimes pays to know the quadratic formula. So walk in, renting a movie, and the manager there is actually doing a algebra 2 problem. It's like, oh dang, what's that darn formula? That formula is like it has a b in it. Like, oh yeah, that's right. That's -b plus or minus square root of b squared minus 4ac over 2a. So she writes it down like, that is so awesome. I'll let you have 3 free movies. Just get whatever you want.
Oh, yeah.
Yes. Knowledge is power.
Whoever said, how are we gonna use this in the real world?
Yeah.
Right, exactly. Walk around always having the quadratic formula memorized. On my other experiences, when I was in graduate school, I went over to the Porta Subs, which was right across the school. And it was the day that I had to eat. So right between the classes, I would go and eat and then come back to class. And so it was 20% off day. That's cool. So so the lady's making the sub, makes it, and I got 3 subs. She makes it, she rings it up, it goes, oh, it's 20% off day, but there's 3 of them, so that means it's 60% off. It's like, yes,
Yes.
I'll take 2 more.
Yeah.
No, I told her, no, it's still 20%. I told you.
I would have.
Oh,
thank you.
I'll take my discount if I get 2 more.
You would have started from it and like.
Oh, these are free.
Yeah.
And then you get 2 more after that.
Yeah, if you get 2 more, then it's all free.
Yeah, then I have to-
Then they have to pay you.
Pay you for it, like rent or something.
I will take 500 sandwiches.
All right, hopefully you guys put it in here. I assume you guys can put in values there. So we're good there.
Hard, but-
Plug it in. And the answers are something about a square root of 3 on top somewhere there. Is that right? And a 2 somewhere there. So let's try it here. So I got this little multiplication here. -4 times 2 is -8. Times 1 is a +8. And then 4 plus 8 is 12. Everybody good there so far? What I usually do is I keep that little guy alone by itself, and who cares about this guy? I just multiply this part together. So -4 times 2 is -8. -8 times -1 is a +8, and then you bring in the 4 afterwards here. So that's a little one to sort of calculate here. Okay, on this one here, 4 is 4 times 12 is 4 times 3. So the 4 gets to go out as a 2. And here's a little thingamajiggy. I'm not sure if you guys know from algebra here. If you have a quadratic formula, the 2 top numbers can reduce with the bottom number here. What we do is we just reduce all 3 of them at once. So technically you divide through by -2 everywhere, as long as you can reduce all 3. We good? I think that was a quick little trick in algebra, as opposed to factoring out the 2, and then the 2 reduces with the 4, and then multiplying it back in. Such a long way to go. So reduction by 2 everywhere, we should get an answer of -1 plus or minus √3/2. You can write it like that. That is perfectly fine. All right, or you can write them as 2 different answers, right? Because there's technically 2 different answers here. And if you were to punch it into the calculator, you would get 2 different numbers. Okay, so there's quadratic formula. Reminder of quadratic formula. And since we're in trigonometry, really don't write the next slide. Not even if if you have a total desire to still write what is on the next slide, don't. So then we have this.
Oh, I have no desire. to-
Okay.
I can't
I already
see
have
that.
that. Yeah, there it is. I couldn't.
I
if
made them
wanted
small
to.
on purpose, so no one writes them down. So all it is we've gone so far, the cofunction theorems, man, the supplement to angle identities, all the good stuff. I'm going to just stop there. We're good. So all the formulas we have so far, let's start. So trigonometric equations, let's jam. So example 4. So let's start off with degrees first, because remember we can put them in degrees or radians here. So solve this equation, and I want you to solve it in 2 different ways. First, solve it for all the degree solutions possible ever in the world, and then solve it from 0 to 360 degrees. There may be a little problem here, because you know how the sine function goes up and down, right? So how many times would it hit 0, or how many times would it hit the x-axis? Infinite amount of times. That's no fun listing all those. So we've got to figure out a way to
Yeah, that would be.
listing it. Yeah. I think we can figure out a way to do that here, but let's go for it. First things first, what we learned from algebra, can you get cosine theta by itself? That's what I want to do. Using the addition property of equality and the multiplication property of equality first. Oh, that's right, I have to work here. Better work with that now. All right. I think we go like this, is that right? Add 1 to both sides. Cosine theta is equal to 1, divide by 2. Voila, I think I'm close. And then we have to think. This is where we start thinking. Or just have a unit circle in front of you, one of the 2. So in my unit circle, I have this, and I'm thinking, when is all the different times cosine theta is equal to 1/2? There we go. Anybody got a unit circle? Anybody have a book? There you go. Thank you so much. 60 degrees, cosine, yeah. So I got this guy here, that's 60 degrees. That's when the x-axis is 1/2. Perfect. I don't care about the y-axis because I'm dealing with cosine. Cool. Any others? Go ahead, go ahead.
Yeah, I said the-
60 degrees.
I did, I just thought the
I thought I heard him. Let's see, if it's 60 degrees, that means you can make the same triangle on the other side, right? You can always fold these out here. So then there should be another triangle right here that has the same exact x value as 1/2, except this guy is now 300 degrees or 60 degrees shy of 360. Again, cool. Okay, so technically what we're doing is, hey, we're going backwards, right? We're going from ratio back to degree value or radian value. So technically we're doing this. Theta is equal to the inverse cosine of 1/2. We're getting back to our angle values. We do it, it's so much easier just to do it off of the unit circle though, than trying to compute it. And we're gonna get to the calculator portion in a bit here. But we got that here. So now let's talk about this here first. Angle, or answer for A. I want all the values ever that makes cosine give you a 1/2 ratio. So let's see. First one is 60 degrees, right? 60 degrees. Now I got to think about all the different ways I can go adding 360 to this guy forever. Is that right? Then I got to think about all the ways of subtracting 360 forever. And I don't want to list them. Not today.
You totally could, but like.
But not
depends on
today.
yeah.
360 degrees. What we're going to do is we're going to do this and we're going to put a little k next to it. Lowercase k, uppercase k. It doesn't matter. We're going to define k in just a little bit here. And then we're going to say 300 degrees plus 360 degrees k. And we're going to say where WH, let me do better than just some chicken scratch here, where x is an integer. So let's talk about that here, see if that makes sense. If k is 0, let's do the 60 degrees first. If k is 0, that means we get our 60-degree angle. We good? If k is a positive 1, that means we just take the 60 plus the 360 makes 390, and we got ourselves a full rotation. We good? If k is 2, that means we got 2 rotations going forward. We good? And voila, I just listed all the infinite possibilities. It's kind of cool. Oh, hold on. How about the negative ones? If k is -1, right? Because k is an integer, right? You can go negative, positive. K is -1. That means, let's see, 60 minus 360? Negative 300. So that means it gets me this one going backwards. We're good. And then if I go -2, that means 1 full rotation plus going backwards. Okay, are we good? Did you guys know, just back to algebra days, did you guys know whenever we graphed something like this, right? Something like that. And we made this line. So name me all the different possibilities. Actually, now make it easier for you guys here. Here it goes. Solve this. Back in the algebra days. Solving it would require us to write down all the answers for x's and y's, right? So if we do that, like 3, 0, is that an answer for this guy? 3 times 2, yeah. 0, 2, is that an answer as well? Yep. Let's see, then we have 6 times -2, will that also be an answer? And this can go on forever, is that right? Just real quick here, that's make sure that's 12, right? 12, then that's a -6, and 12 minus 6 is still a +6. We're good. So the reason why we graph a line is to show all the different possibilities, right? That's the whole point of it, because you can't ever write them all down. And once you make this line like this, you're saying, hey, anything on that line are all the answers. And if those lines look exactly the same, that means you have solutions that are exactly the same for those equations. We're good? So that's that little graph there. Not going to do the graph here. All we do is we just list them with k values. Okay, and then the easy one, I think B is actually even easier to do before. I don't know why the book does it backwards here. But if you just go from 0 only to 360, and notice it, you're not including 360. You're including the 0, but you just start just, or stops just shy of 360. We're good? Answer, 60 degrees and 300 degrees. Are we good? Boom. What do you guys say? Simple enough? That pretty good? Okay. To be like really, really sophisticated, impress me and all that stuff, instead of writing k as an integer, what you can do is you can just say k is an element of, and this is the symbol for integers. It's like a z with an extra slash down the middle. There's your. And
why are we being asked to solve from 0 to 360 if we just solve for all? Like, isn't it obvious that we know what it would be from 0 to 360?
eventually, when we get to, so real quick here, Georgia, this question is why solve for infinite, and then picks some solutions here. Trig books in the back, in the past, what they've done is they've done A for a long time, give me all the answers, right? And then when you get to the application questions, then you can only do one full rotation, right, of something like a lighthouse spinning or a road going around in a circle, right? So you're only going to find out one. So usually what happened in the past is for this theoretical part, you find all of them possible. And then for the application part, you find some. And then later on, trig books decided they're going to at least give me one full rotation just for the purpose of understanding it. For me, it almost like it works backwards. It's almost like part B you can do first, and then do part A and then be done. Yeah. Okay, good. Ready for yours? All yours?
Wait, so then what is like why K? It's just like we just chose a letter to put K.
Sure. Yeah. We have to somehow define an infinite amount.
So that's what K is.
Yeah. And K is defined an infinite amount. When you say K is an integer, you're saying all the integers in the world work as long as you plug into this little function.
Okay.
And kind of funny little thing, if you guys realize from your geometry days, do you guys remember drawing any kind of like triangles and stuff, right? Remember triangles at the vertices, they were always capital letters, right? We had A, B, C, right? And in the spectrum of mathematics, it's kind of funny. A, B, C are usually constants, or D, or whatever it is. The beginning of the alphabet are numbers that stand for one particular, or variables that stand for one particular number. We good? If you go back to the end of the alphabet, X, Y, Z, those guys stand for variables, things that could be whatever it can, whatever you want it to be. We good? And then you got this little middle ground, H, K, J, I, and those in the math world, they stand for stuff like this. They stand for a value you can use. You define it inside a problem so that you make an infinite set, or you go on for an infinite amount, or index that goes on forever or to a certain place. So there's some logic to some math stuff here. Okay. On your mark, get set, go. All right, cotangent, all yours. Have fun. Just not too much fun. All right, cotangent and tangent, they're kind of funny because they don't appear on the unit circle right away. And remember, there was a little trick that we've done in the past. Gets us back into the unit circle right away. I'll let you think about it for a little bit. All right, let me start it as well here. I think we'll end up at the same spot. Adding 1. Then dividing by √3. And if you're here, you can actually just stop right there. Boom. Okay. So we're going to try to find the cotangent ratio that gives us a 1 over √3. Anybody remember? What's the little thing that we do in order to get back into unit circle? What? You forgot? No, I have not taught you well yet. On the unit circle, the denominator is always 2. That's right. So what we do is we just put a denominator of 2 here. So this is 1/2 over √3 over 2. Once you put that denominator of 2, then you're looking for a, let's see, cotangent is what again? Is x over, yeah, I'm looking for that right there. I'm looking for a positive, oh, hold on, I'm looking for a positive 1/2, positive √3 over 2.
Or negative.
Thank you, yep. Because it's a fraction, the negatives can be canceled. So then I'm looking for a negative 1/2, negative √3 over 2. And when does that happen? Awesome. 60, right? 61st. Right here. So I'm looking for the x and the y value. And then all the way down here, boom, negative 1/2, negative √3 over 2, perfecto. Love it. Okay, so this is 60 degrees here. It's gonna be 60 past 180. Dylan, you said 240, I believe, right? 240. Awesome. Okay, are we good with 240? Okay, so let's write this out the long way here. So it's gonna be 60 degrees plus 360 degrees K. Then we have 240 degrees plus 360 degrees K. And I'm going to use this one. Is that okay? Just easier. Mathematicians are lazy. They just put in the symbol. Why write out in English if you can just write a symbol for it? But K is an integer.
Understand. So.
Okay, that's true.
I don't.
Let's do this in multi-part.
Okay, and then real quick here, bless you. Can you condense this down anymore? So notice you're going around 360, and it only works for tangent, it only works for cotangent. Notice they're only half a rotation apart from each other. We good? So they're half a rotation apart. Instead of saying it's 60 plus 360, then it's 240 plus 360. Any way to condense that down so it's just one single answer. Try it. Go ahead.
Plus 180.
That is awesome to me. That would work. Okay, there's the other answer. So both of them are correct. The second one is a more condensed version. Again, only going to work for tangent, only going to work for cotangent. Because your answers for those are always going to be 180 pieces apart. Oh, remember when we were doing graphs? Remember how tangent, cotangent had a period of pi, right? Instead of 2 pi, right? It would start cycling earlier. Okay, so there's that. There's part A. Part B, going from 0 to 360, that's easy. Theta is equal to 60 degrees, 240 degrees. Done. Okay, I think we have enough time to get through them. Okay, yours, I think you have everything necessary. Let's go with it here. Oh, that's right, we got to change to radian measurement now. So on your mark, get set, and go. Changing things up to radian measurement. And now we get to scoot. We should be scooting over our trig functions. All right, give you guys 30-second head start. Go for it. Can you at least solve it for just sine of t? So sine of t equals something. All right, and I'm thinking because you have sine of t on both sides, at least I'm gonna put at least that together here. So let me move the sine of t so it's just on one side. So that allows me to cancel. Square root of 3. -2. Ever good with -2? Cool. Divide through by -2. Voila. And then I can switch these around and just so it looks nice here. So sine of t is equal to -√3/2. That's what I'm trying to solve for. Be very careful in the homework if you're in degrees or radians. So off the unit circle. Anybody give me the radian angle measurement when sine is -√3/2? Pi/3? Pi/3 is up here, right?
Oh, wait, yeah, never mind. Thank you.
4/3, perfect. I think down here, this is 4/3 is that one. And 5/3, right? It's just shy of, and let's see, move this all the way around like this, and it will give me 5/3. That's cool. Okay, A again. Let's go with 4π/3. Notice they are not 180 degrees away from each other, so I'm going to have to put 2πk. Let's see, and some books use a uppercase K, some books use a lowercase k, so it doesn't matter. Just pick one, stick with it here. The only thing is, you do have to stick with uppercase or lowercase, because once you go with something, you got to go with it here. So this one, then we have 5π/3 plus 2πk. All right, where k is an integer. I won't impress myself. I'll just write down k as an integer. And the b value, let's see, just to say it correctly here, we should say t is equal to 4π/3, 5π/3. Ooh, first time I did that. Okay, and then the toughie, a little bit of a toughie here. Got to do the calculator one. Okay, talk to me. Is 6 okay? Okay. 7. Dun, 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 dun. Solve for the degree value. We're going to use a calculator. We're going to round off to the nearest 1/10 of a degree. So if you brought your calculator, great job. If you didn't, I'll see it on Monday.
Leave the class.
Now you are done.
I looked at my calculator and I was like, you know, I probably don't need it.
That's pretty stupid. I want to share that you do need it.
Yeah,
Yeah.
making a conscious decision not to bring it.
Yeah.
Basically, every time I haven't brought the calculator, I needed it. So
What if you just,
maybe there's a lesson in there, I don't know.
what if you just always brought?
Whoa.
But that would take effort.
Yeah.
Sure, you can't have that much effort.
Always be effort. No.
So solve for all degree values here. And then again, from 0 to 360, let's go with it here. This one's gonna be a little tiny bit different, so let's go with it. So subtract 3 from both sides so we can finish on time. Got a -3 over here, divide by 4. And I'm looking for when sine gives me a -3/4. Ah, gotcha. Okay. So here's remember, let's talk about this here. So theta, if I were to go like this, right? If I do this, it's gonna put me into quadrant 4, right? But it's gonna put me in quadrant 4 the negative way. That's my problem. As opposed to, I need to be between 0 and 360 when I finish this off. Okay, so here's what we do. Dun, 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 dun. We forget about the negative just for a little bit. So forget the negative. On your calculator, you're gonna punch in sine inverse of positive 3/4 and make sure you are in what mode? Degree mode. So give me that value there to the nearest 1/10 of a degree. Something like 20 something or no, or 40 something? 40, cool. 48.6 degrees, we are good. Okay, once we do that, now we talk about what we need to get to. So let's finish off, I got 2 minutes left. So what we've just learned is we have theta. Oh, theta with the little hat on top, that's what we just learned. We haven't got theta yet.
Okay.
We've just learned what it does in quadrant 1, and we've learned the reference angle. Good. So now, because sine is negative, which 2 quadrants should sine be in? 3 and 4, yeah. So I have a triangle set up in quadrant 3, I have a triangle set up in quadrant 4, and it has a reference angle of 48.6 right here inside this little angle. It also has a 48.6 inside here. So now the question is, what is this guy? And how do we get there? In quadrant 3, what do we do? Yeah, in quadrant 3, we take 180 degrees, we add the king. And we get ourselves 228.6. That's cool. In quadrant 4, da 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 da. Ooh, what do we do in quadrant 4? All right, and we're out of time almost here. 1 more minute left. Yes, 360 degrees minus the king. 360 minus 48.6 and 311.4, I believe, are the answers here. Boom. So let's go with it here. Answer to A is 228.6 degrees. 311.4. So 228.6. This is funny. Degrees plus 360K. 311.4 degrees plus 360K. K is an integer. And B is just those answers again. And I'm going to let you guys go so you don't get late for next class.
Not our reciprocation.
Yeah, it's really okay.
Watch you there on time.
You wanna-